toy models, which seem to be suggesting that physicists also are not completely, sometimes think that physics is complicated. Everyone since von Neumann has been trying to construct these toy models. So I'm going to try, so some of the methods I think for constructing these toy models arise from logic, so maybe I'll have to say something about that. Is this reasonable? I'm opening the last random version because this one has probably been sitting there since the morning and somewhere halfway through it will die. Alright. And it's very much work in progress, so I hope the ideas are worthwhile, and some of the details will probably be changed as when I work them in more detail. So I'm first going to tell you about how to, some logical tool which may be useful to construct some toy models, or to reconstruct some existing toy models, and then I'm going to try to say what, try to maybe specify what the toy models that we construct using these tools are trying to achieve, or how I understand that what people are trying to achieve with these toy models. And maybe I'll show you what how we can do that, and at some point in time we'll work. So a very basic logical principle which we can use: comprehension. Someone gives you a predicate, or if you prefer to call it a characteristic function, and the comprehension gives you the subset of elements satisfying that characteristic function. And then you generalize that all the way up to all kinds of categories. So if someone gives you an index set, you can perform the same thing, and as it turns out, then all the functions going into A are in one-to-one correspondence with sets indexed over A. And then if someone gives you maybe a set indexed over a category, or over a topological space, or a manifold indexed over a topological space, you may want to glue these pieces together, and that's how sheaves came about, even before categories came about. So this is then comprehension for pre-sheaves is a standard thing that they do all over topos theory. You start from a pre-sheaf, and then you construct the total category of that pre-sheaf, and that is useful. If that pre-sheaf is a sheaf, then this total category gives you the corresponding local homeomorphism. And it goes further. If you have an indexed category, that is one-to-one correspondence to a certain family of functors into that category, which are called fibrations, in analogy with fibrations in topology. And while I'm talking, maybe you are observing how the constructions slightly generalize underneath. Each of them are based on the basic thing that you take all these pieces and you glue them together. Maybe I should have put the absolute value here, because each of these phi x's is a category. So to get the objects of this total category, we take the disjoint union of all the objects of the fibers, and then home sets will be pairs, a morphism from a pair xx to yy, where x is an object in the base, and little x is an object embodied in the category corresponding. So a little x is an element of phi x, so the category phi x. So then a morphism from one pair to another will be pair of morphisms, one in the base C from big X to big Y, and another one in the fiber, which is a category. So you're blowing these things up. It's not, you know, probably not worth trying to really zoom into what is going on. It's very similar to that thing which we started from, comprehension. You know, it's very similar. You glue things together and then take the witnesses. Or if someone gives you an index set, you glue all these sets together and project the disjoint union back to the set over which you started indexing. And this is due to Grothendieck, and this great historic movement got completed by Samson and Dusko in 1996. Now, I mean, you then observe that you can actually take any functor into R, and there is one-to-one correspondence from functors from any category into R, and lax functors from R into the category of spans, where we need to say that fibers are small and so on. What we use this for is actually to specify interaction categories, which were the maybe not grandfather, but the father of these dagger compact categories. They were compact categories, and most of the time you actually are using this lax functor into relations, and then you're getting a faithful functor into the category which you started from, and again you're getting the objects of the category which you construct as disjoint union of the objects of your fibers, and you reconstruct. So a morphism from a pair XX to YY will be a relation from X to Y, which will relate little x and little y. Very simple. So at this point, it's a very, very simple construction, and I say that we can use it. Why is it useful, actually? It is useful because you can lift structure from the base. So if you start and you can combine, you know, if you start from the base category, which has some structure, and if your fibers carry some additional structure, then you can build this total category. Your local homeomorphism will have interesting structure which you have specified in these fibers. For instance, so here's the general way of lifting that structure. So you end up with a, if the base category is, let's say, compact, and if your fibers are some complemented lattices or monoids with an involution or something like that, then you combine these two things to get linear structure on your category. So the duals in the fibers and duals in the base are going to combine into a duality, and you lift the tensor. These are arrow parts of the functors on your fibers, and you end up this duality, and this tensor give you another tensor. And this is the kind of structure which comes about all over the place. So let's see where it comes about. So before even these linear categories were defined, well, no. Barr has defined these star autonomous categories in the 70s, but very early on, before they were really popular, in the very first presentations of quantum group, Manin had constructed a very basic category using this construction. So just as an exercise to give you an intuition, what happens, you just assign to every vector space, you assign the lattice of closed subspace. Well, let's forget about the topology. To just an arbitrary vector space, you just assign the lattice of its subspaces. Okay? You glue it according to this you glue it according to the lifting construction. It would be Grothendieck construction if it were index category, and you end up with two monoidal structures. So your objects will be vector spaces with a subspace. The dual will take it to the dual space and the annihilators. Okay, and you end up with two tensors. One tensor will tensor the subspaces, and the other tensor will go to the annihilator of the tensor of the annihilators, which is much bigger space. So you have non-trivial structure in this category. Or, okay, so we'll be building these toy models in an even simpler world of relations. So that some of these so the point is that some of these non-trivial structures that we see and use from vector spaces and Hilbert spaces can be found rather cheap in categories as humble as relations. So the simplest instance of lifting, of taking a relator, of specifying something and then lifting it into a total category and getting a non-trivial linear structure would be if you just take relations and map every set into all its subsets. So you get the fibers will be all predicates, and a relation will be going from A to B. If so, a relation will be a morphism from XA to YB if it's a relation from X to Y, which maps A into B. And again, we get non-trivial linear structure, and this is all as warming up, so that we try using it to see what we can do with this. So let me. So now I've said this is a tool which we may possibly use. So now what for? It has been my impression that when we are trying to build models of quantum computation, the main thing is to recognize classical data in this quantum universe. If quantum universe didn't have classical interfaces, we would have no problem with it because we could never observe it. The problem which we have is that we want to, if we want to compute with it, we want to stuff some of our classical data into this quantum universe, use some quantum resources, and get some classical data out of it. And the trouble is how to distinguish what is what. What is our classical data that we want to, how do we want to represent them in the quantum universe? So the question is, how can we recognize, so the question I'm saying that is addressed in the standard model, and the question which somehow toy models are trying to answer in their toy little way is distinguishing classical data from quantum data. And one simple-minded idea is that since we know that quantum data cannot be cloned or deleted, classical data can be copied and deleted, so maybe that might be used as a distinction between the two. But then, you know, really in a program, when I'm really writing or analyzing a quantum algorithm, how do I tell apart classical data? So what do quantum programmers really do? They begin from a classical function. So I want to compute, I want to decide something about the values of a Boolean function. And then in order to represent that Boolean function by a unitary, I'm going to first make it into an involutive function, because only involutions will be represented as unitaries in a straightforward way. So mind you, this mapping of bit strings into bit strings now became mapping on the indices of your basis vectors. So that in a way this classical computation, which like quantum computer will implement, is happening on the basis vectors, but the basis vectors are quantum data, and I should remember that my classical data are just indices. And then we do the quantum parallelism thing, we superpose things at the beginning, and maybe we superpose them in the end, and if we want to decide whether a bit string, whether the function is balanced or not, for instance, then we can look for the period of the function and for the hidden subgroup. So here's the summary of the quantum of probably the first quantum programming software design pattern. So you begin from a Boolean function, you make it into an involution, you represent it. So this is the crucial step. You go from this classical world, you represent your classical data as quantum data, you superimpose them, you read something. Whenever you run this, you get one linear equation in x and z from this representation. So you only need to run it m times because you can get the period from m equations, while classically you would need to run it. You would need to run it 2 to m times on all of the inputs. So that's the pattern. So what comes out of this is that actually in this pattern, how I annotate my classical data and how I remember what are my classical data when I package them here is by writing down these variables. You see, I take this variable x and here I must copy it. So it must be a classical thing. I copy x twice. So the answer which I'm going to try to sell to you is that classical data are just what's denoted by the variables. And so let's see what we can do with this idea. How do we adjoin variables? So we've been doing this quantum physics categorically, so let's take some leverage out of it. We know how to adjoin variables to algebras. Everyone knows how to build a polynomial, how to adjoin a variable to a ring, and to build a polynomial ring. And this is the universal property which characterizes it. So a polynomial ring is universal among all rings. So if I give you a ring homomorphism into another ring and tell you where to map your variable, you will know exactly it will determine a unique ring homomorphism out of your polynomial ring. So you can do the same thing for categories, say Cartesian, and that's been done a long time ago by Lambeck, and it's been built into the foundations of semantics of functional languages. So how do we go about this? What if we throw a variable into this quantum universe represented as a Dagger compact category? So Dagger compact category, as Bob has been telling you all these years, are a bunch of pictures, and they go back to Penrose's ideas and to Joel Street's ideas, so that something like this homomorphism would be something like a picture of this kind. Your component morphisms would be the boxes or nodes, and your objects would correspond to the threads. Okay? And to throw a variable into this world, you just need a special kind of vector. Okay? And you annotate them because you want to manipulate them. And the thing, why do we use variables? You know, when you're writing a functional program, what do I need variables for? Well, I need variables for polymorphism, to be able to abstract over these variables. So if I throw in a variable into a Dagger monoidal category 1, it is a completely defined thing, but by that universal property, which I've told you that polynomial ring satisfies it, and polynomial category satisfies. Okay? What do I need in order to have anything of this is the abstraction operation, to be able to really copy and delete these variables, to move them around in the category. So in other words, what you're looking here is a morphism in the polynomial category. It is generated by morphisms in your category and by the variable, just like in the polynomial ring. It's freely generated by these operations. So how can I manipulate? What structure do I need in my category to move these variables? Well, in order to be able to bring them all together, I need something like this comonoid structure. So this is the geometric idea. In other words, we need something that Bob and I have used to call classical structure, and now, since, as you will see, they are neither classical nor they're unique, they correspond to basis structures. So for about 15 minutes we've called them basis structures. Now Bill is calling them observables, and probably they should be called Bob structures or something like that. In any case, the least you need to have there is that they're Bob. Yes, Bob. I mean, it's quite appropriate. They are comonoids, so they are like monoids turned upside down. A monoid is something you give you have an operation, you give it two things and you get one thing back, and a comonoid is you give it one thing and you get two things back. And similarly, it has a co-unit. You give it something, it destroys it, as opposed to the unit. And you get these, if you work through your structure, you get these by the abstraction. And if you work through it, it will be associative. That is why it's comonoid, because monoid is associative. And moreover, what you want from it is that your old variable is real. In other words, that either its dual is its adjoint, or you may say that it is equal to its own, to the lower star, what is it called? Complex conjugate, yes, to its complex conjugate. Equivalently, you can say this by saying, so that here's a little theorem. Equivalent with the statement that the variable is real is the statement that this structure, that this comonoid structure, the Frobenius algebra, is making the object X self-dual. In other words, it's giving it an entangled pair and inner product. Or more equivalently, more equivalent versions, the most elegant one is due to Carboni and Walters. And this is the Frobenius condition, which is familiar to you. So what I have tried to convince you by this story is that the point of constructing these toy models is to distinguish within your quantum world, which we say can be very softly defined as a Dagger compact category, to distinguish in this world these classical or basis structures, which will be Frobenius, which will be the suitable Frobenius algebras. So how can we do that? Okay, why is this important? Well, in the standard model of Hilbert spaces, you have just captured what you have been used to call classical data type all the time. Well, how much?
Got about 5 minutes.
Okay. I'll get to the point in 1 minute. These classical structures are in your standard model just the basis. It becomes funny when you look at what you would expect to be a fairly trivial model, relations. It is a compact category and it has a very, very trivial adjoint. And then you look and try to characterize all the possible classical structures, and they turn out to be not just what you use to recognize it as the usual Cartesian diagonals, but any disjoint union of abelian groups will do. So if you have a, let me see, did I work it out? If you have a set X, you partition it and you specify an abelian group structure on each part. If you take each element to the set of pairs, which in abelian group evaluate to it, you're getting a classical structure. And there are very interesting non-trivial bases for that. So what's a basis vector in these theorems? A basis vector is just something that your classical structure can copy and delete. And you can also abstractly specify, so Bob and Ross have, in terms of representation, specified what unbiased vectors are. You can also spell that out internally. So you've got each classical structure has its basis, and each classical structure determines unbiased vectors into which you may transition to use quantum parallelism. So that then you can start looking at relations as a toy model. And indeed, as Bob and Bill have shown, Specken's toy model is just that. It is just a part of the category of relations. So if I give you a classical structure, so that is this disjoint union of some abelian groups, so it consists of two things. So first of all, this partition is just the basis. So a basis vector is just the underlying set of this abelian group. Okay? And on the other hand, a vector, a subset of your classical structure, is unbiased with respect to this basis if and only if this should be intersection. Its intersection with each basis vector contains just exactly one vector. So, in other words, bases consist just of partitions. So just in order to generalize it, I'm specifying here, this is just the notion of partition, which everyone knows. It's a set of disjoint, mutually disjoint sets, each is non-empty and they cover it. So a set with a partition is a basis space. Let's comprehend it. Okay, so once again, this basis structure which consists of abelian groups is giving you two things. I say that the partition which it's giving you is the classical data. On the other hand, the group structure which it's giving you, it determines the entanglement which is induced by this structure. So for the moment, let's forget about the entanglement and let's comprehend just the basis. So let's look at the specification at one of those functors, sending each set to just partition something. So this will be the basis with respect to some classical structure. So I'm basically doing the same thing which could be done by sending a vector space to the basis on it and gluing sets over vector spaces. I wanted to write it up, but wouldn't have time to present it anyway. And then you glue it according to this comprehension schema which I've shown you before, and you get a very nice structure. Mind you, now we're going to start reconstructing what we've known, or what people familiar with test spaces have known as quantum structures all along. So first of all, you want this dual to go to a complementary base. What might that be? And you do have a tensor. So here tensor would be, so this is E times Y, so this is inverse images, E times Y and X times F. And we are reconstructing the second tensor. So what will these complementary bases be with respect to these basis structures in REL? So what am I doing for you now is I'm trying to answer the question: if you want to implement quantum programs, say that Simon's program, by just using non-determinism, by not using anything else but relations. So what would be your classical data? And I say your classical data would be determined by just having some group structures over your partitions, and this would give you basis, these partitions would give you basis, and your little Fourier transform would be going from this basis to unbiased basis or to incompatible basis. And what would that? So now we're going to spell out what these incompatible bases would be. So this orthogonality relation means that every two elements of each of the partitions have intersection which contains exactly one element. Okay, and on the other hand, it's obvious more or less that partitions form a complete set with respect to partition refinement, to a complete lattice with respect to partition refinement. So we would like to then define this complementary basis of the basis. But the bad thing is that the join of this lattice doesn't preserve orthogonality. The fact that B and C may be both orthogonal to A doesn't buy me anything about the join. So what I can do though is prove that if I take two maximal orthogonal sets, okay, then these partitions must be isomorphic. So there must exist a bijection of underlying sets which will map one partition to the other. So up to isomorphism, I can then define this antitone operator, the duality, and then I'm in the business, and it is easy to see that it is involutive. And now I'm in the business of spelling out this structure explicitly, and at least in the structure which Alex would call semi-classical, I think these partitions are semi-classical. I get for free out of this duality, I get the rather complicated. So how I would say this is out of logic, because basically all of this is just lifting pieces of logic, combining, gluing pieces of logic in the basis and in the fibers. So this part is obvious. After we have defined the dual, you are getting this rather complicated Foulis-Randall tensor as the dual of the thing which you started. Okay, and then we can continue generalizing. So let's drop the requirement. Okay, and then we can do that for test spaces and start reconstructing by using the tools of lattice theory over. So this is, suppose I have constructed by this comprehension, gluing construction, I can construct the category of test spaces. I can reconstruct the two relevant tensors on it as well, and then we can start sort of abstract logical reconstruction of what Alex and Barnum and a couple of other authors whom I can't name now have been doing in these abstract probabilistic theories, because you basically so morally you could think of this as the constructor of so think of this as double power set. So okay, I'm done. Thank you.
Any questions or comments? Not that we have time for any of this. Alex?
Well, I just have one question. It's actually about this last slide.
This?
Yeah, if test is supposed to be the category of test spaces, maybe?
Yeah.
Then on the right, this object, affine functionals on the state space.
Yeah, it's just abstract definition of that same thing. Substitute, so I'm applying it only to this. So it's just reconstructing,
Yeah.
It's the only thing it's pointing out, this is just from your paper, but what is being pointed out is that it has a monad structure.
Okay, the only thing I want to say is that test spaces as usually defined wouldn't normally include that object on the right.
This object? You mean this object?
That object.
Well, it is just a set, and here
Yes.
I'm
What's
spelling
the
out.
what is the covering?
Here.
Yeah, and the problem here is that. Oh, I see. So you're just taking subsets. You're not
Yes.
you're not taking index sets with repetition. Okay, so that's fine.
It's falling there.
You guys can discuss it.
Yeah, it almost works. It almost works.
Perfect.
Okay, let's
Well, let's thank Dusko again.